Today we continue on with the topic of rigid body rotational dynamics, and where we need to go today is to try and generalize a little bit more so we can deal with slightly more complicated motions. And one of the things you realize if you stick around in mechanics long enough is that rotation of an object about one single axis that we can then set as the z-axis and keep as the z-axis is actually kind of rare, and often rotational motion is a lot more complicated than that. Right up to the point where, when we get later in the lecture, we actually set up a new set of axes so that we can keep x, y, and z for setting up our space and then attach a set of axes to our rotation. And to give you one good example here, you can buy sort of these really nice gyroscopes online, and you basically have a disc, you run it up to a very high speed using a high-speed electric motor, and then you can put that on sort of free-axis gimbal structure and have a look at some of the interesting rotational dynamics that happen, okay? And so one example here is what we call precession. So you basically have your disc spinning, you put it on a free pivot point, and it will sort of fall out due to gravity and then spin itself around, sort of chasing the torque that's coming from the torque that's coming from it trying to fall over due to gravity, okay? And so you'll notice here that it's actually very hard to define a single constant axis in this rotation, because the rotation that you established in the first place now is changing its orientation, its axis is changing orientation as a function of time, okay? So we've got a lot more complicated thing turning up in here. And so what it means ultimately is we need to get a little bit more complicated with our idea of inertia, okay? So if you step right back to first year, your concept of inertia is very simple. You have a moment of inertia, it's one thing that's associated with the body, and you can do that mostly because in your first year courses you handle really nice objects that, you know, have favorable symmetries that allow you to only worry about the moment of inertia, about that one axis, okay? And as we showed yesterday, if you get more sort of detail into this, you have products of inertia which are components in other directions that begin to play an important role if the symmetry is not ideal for that system, okay? And the ultimate result of that is that we obtain an angular momentum vector that is not always parallel to the angular velocity vector, okay? So when we go from having rotation about one fixed axis, which is what we did yesterday and showed, you know, we break the symmetry and things get more complicated, now what we need to do is adapt to the fact that that axis is not necessarily fixed either. And the way we do that is to basically turn inertia into a tensor quantity. And for everything that we're going to deal with here, it's basically going to be a 3x3 matrix that contains our moment of inertia and also products of inertia, okay? So we're going to build this up into a more complicated thing that takes everything together. Let's get some expressions for this, and where we're going to start here is with the angular velocity vector. So we have our vector omega, and as we said before, it basically points along the rotational axis given by the right-hand rule. And whereas yesterday we had a one fixed axis which we called z, and it always stayed z, so we could go, you know, this vector is 0, 0, omega z. Today we have to generalize it. So it's now going to be omega x, omega y, and omega z. And it's not even necessarily that it can have three components that are fixed. It could even, in some cases, have three components here that are time dependent. So the axis of orientation can be changing as a function of time, and we might have to build that into some sort of problem. All right, so the next step here is to look at the angular momentum. And you'll remember that it is mr cross v, and of course we're dealing with a rigid body made of a number of components, so we can write this thing as the sum over alpha, m alpha, r alpha cross v alpha. And we have our usual expression for v of alpha, which is omega cross r alpha, And I'll remind you again, this is the one exception in rotational dynamics where the radius for a cross product is on the right, not on the left. Okay, and in a second you'll see why this is important. So this thing now becomes sum of M alpha, R alpha cross omega cross R alpha. And you'll notice something kind of interesting here. We've got two cross products. We've got something that looks like R cross omega cross alpha. If you think about this for a second, imagine we rearrange the terms here. So what we had was R alpha cross omega. What would happen there is you've got the cross product of R alpha with itself, and as you all know, the cross product of a vector with itself is always 0, right? So that would mean that the angular momentum is always 0. And again, if you put the two R alphas on the end and the omega up the front, you would get the same answer out. So it's actually kind of significant that the omega turns up in the middle of this, because it's the one thing that stops that cross product from collapsing to 0. And it's also, for me, one of those reminders that, V is the one case where the R is on the right-hand side, okay? And this is sometimes one of the nice things in physics as you go along. Rather than trying to remember equations, you try to remember why equations are the way they are. And this is one of those examples. I kind of know that V is the one place where I have to put omega on the front, and I have to put it on there because of this concept of the double cross product in the angular momentum collapsing to 0 if I don't, okay? And so then I no longer have to remember it, because I just know that this is why it works, rather than having to memorize that it works. And in a lot of cases, this is one of the good ways to get ahead in physics, is actually to understand the equations rather than try to remember them, because it means your mental recall capacity is easier. You just have to remember why rather than what. Okay, so step in here is now to do this cross product. And I'm going to go halfway because it's going to get ugly really quickly. What we have here is R cross omega cross R. And I'll do the first one, and then I'm going to kind of walk a little bit into the second one to set it up for you and let you do it, because it turns into a mess. So we've got R cross, and then we're going to do our cross product in the usual way here. So we've got I, J, K, omega X, omega Y, omega Z, X, Y, Z, like so. And so this will now be R cross, we can put a set of brackets here, and we can break up these particular components, right? So we do this as usual. We start with I, it's going to be this times this minus this times this. So it will be omega Y, Z minus omega Z, Y. Then the middle one, you do the opposite direction instead. So it's this times this minus this times this. So it's going to be omega Z X minus omega X Z, comma. And then the last one we do, as usual, it's first times this way and then the opposite in the diagonal, right? So it's going to be omega X Y minus omega Y X, like so. Okay, pretty easy, and you should make sure that you're good at doing this and doing it quickly, because it becomes kind of important, particularly for mechanics problems, but in other bits of physics as well. And then now, hang on, let's change color. Now we're going to do another cross product in here, right? And this one's going to be the ugly one. So this will now be, we're going to have, actually, let me get rid of the right-hand line just so I can keep this contained. Experience tells me that when you get these ones, it's actually better to write the fat thing first. So we're going to go omega Y Z minus omega Z Y, omega Z X minus omega X Z, and let me just slide this over. Omega X Y minus omega Y X. Whoop, too close to the edge. Like so. And then our R in here is now going to be X and Y and Z, and we're going to have an I and a J and a K on top as usual. And you would go through and you would do this determinant in exactly the same way that you did the one above, except now you're going to have a huge kludge of terms, And if I do this, I'm going to drive you all crazy writing down all the terms and saying them aloud, and you're all going to go, come on Adam, hurry up, let's get through this. So what I'm going to do is skip ahead to the answer. I'm going to let you do this for yourself as an exercise, and I'm just going to break out the various components as we roll through this, right? So what we're going to have is an LX, an LY, and an LZ. So what I do in my final vector is take the X component, the Y component, the Z component, and just split them off. The X component is going to be sum over alpha, M alpha. And remember, this cross product I did just here is really just this component inside. So I've still got to keep the sum and M alpha that I've got hanging around out the front and bring that down into the components, okay? Of y squared plus z squared omega x minus x y omega y minus x z omega z. Okay, and I'm going to have an ly in here, and it's going to look like sum over alpha m alpha minus x y omega x plus x squared plus y squared omega y minus y z omega z. And I'm going to have an LZ down here, and it's going to be sum over alpha m alpha minus xz omega x minus yz omega y plus x squared plus y squared omega z. And I've just realized I've made a little mistake in here. It's right there where that thing should be a z, because in my top line I've got a y squared plus z squared omega x. In the middle one I've got x squared plus y squared omega y, and in the last one I've got x squared plus y squared omega z. Okay, so you can see there's a symmetry in this which allows me to spot whether I've got mistakes. And again, this is a good tip as you go on doing physics. Sometimes it's good to be aware of, you know, what symmetries should look like so you can spot your own errors when you make them. What we can do in here is break this up now into components of omega x and omega y and omega z, right? Because it's obvious from what we've done before that that's going to be what happens, and you can see them floating around in here. So this would be now what we could call like a ixx omega x plus ixy omega y plus ixz, whoops, wrong letter, xz omega z. And then this here is going to be iyx omega x plus iyy omega y plus iyz omega z. And you can see that the first index is tracking the specific component of angular momentum I'm interested in, and the second one is tracking what component inside that I'm dealing with. And so that's a convention to keep in mind as you work your way through this as well. Z omega z. Okay. All right, so we've got this. And so now we basically do the same thing that you know from your first year linear algebra courses, that you can basically go through now and write them as matrix components that we've got in here, and build yourself up a matrix and handle these equations as though you know, there's simultaneous equations with a linear algebra approach. Okay, so the interesting thing to note here is that we have terms in here that look like ixx sum alpha sum over m alpha y alpha squared plus z alpha squared. We've got that sort of term, like a component times component. It's component squared times component squared, and you'll notice that there's three of them in here, right? There's this one here, this one here, and this one here. And there's also in here components that look sort of cross-term like, and they're sort of minus sum over alpha m alpha x, x alpha y alpha, like so. Okay. Some of you who are really observant at the moment will notice I've already got these written on my slide, and also I've made a mistake in there. This thing at the front should be a plus. I'll fix that up in my notes later, but it's hard to fix in a video, so we're just going to leave it in there, unfortunately for now. But that will be a plus, okay, just so everyone's clear on it. Don't let the perfect become the enemy of the good, Adam. You'll never get anything done. All right. So we have this nice setup now. And the interesting thing here is that we can finish this off by writing the expression that we saw in the last lecture and that you know from first year, that the angular momentum is equal to I times omega, except now it becomes, rather than a vector is equal to one moment, which is a number, times an angular momentum, and then you set a direction for it. Now you know that this thing is a vector and this thing is a vector, and the relationship between the two is basically just a 3 by 3 matrix connecting to 3 element vectors on either side. Okay. All right, so this is actually a good point to do an example. And what I'm going to do is fairly typical sort of exam or assignment or just tutorial problem of here's an object, rigid body, calculate what the inertia tensor is, okay? And in a lot of these problems, what you're relying on is switching from a sum to an integral, because you're now dealing with some continuous object that's continuously distributed in mass. Okay, so make sure that you understand this transition from sums when you're cutting into small pieces to integrals when you're dealing with infinitesimal pieces, because that switch between the two is really important to be able to do. Okay, so let's do this one. It's a neat little example, and then we'll finish and take a break, and we'll come back and do some other stuff in the second half. So this one here, what we've got is a solid cube, side length A, mass big M, and it's rotating about this origin position, which is in its corner. So it's basically, you know, you can imagine it's sort of swinging in a circle around that origin. So it's a sort of a strange motion, right? It's not the cube rotating on its own axis, it's the cube rotating on one of its corners. Problem tells you to use axes parallel to the cube edges. In a lot of cases, questions will give you hints. And then it says, find the angular momentum when omega is along the body diagonal in the direction 1, 1, 1. Okay, so now what we've got is a rotation that actually still is about that point in the corner, but the axis is now driving its way through that object. Okay. So the question's kind of refined itself. It's rotating about a corner, which was an arbitrary motion, and now we've actually set an axis for it so we know where this is going. Okay? All right. So our step in here is basically to get one of the moments of inertia, which you'll notice are basically just these little expressions on the diagonal, and then to get one of the products of inertia, which is these terms on the side. And in the most general case, you would have to get all 9, which is a little bit of work. In a lot of cases, if you've got symmetry in your problem, you can get one of each and build the rest of the matrix up from it, okay? And the nice thing is that most problems you deal with, they give you a symmetry to save you time, so that's all you really have to do. So what we're going to do here is strike out and get a moment of inertia. And it doesn't matter which one we do. We could do ZZ, we could do YY, we could do XX. You can choose. So I'm going to do XX just because that's what's in my notes already. And so it would be sum over alpha M alpha Y alpha squared plus Z alpha squared. And of course, we're dealing in the infinitesimal limit now, so this thing's going to become an integral. So it's going to become the integral over the density y squared plus z squared dv, okay? Where if I take the density and multiply it by dv, I get a dm, right? Which would be my little mass element m alpha, okay? So I've just taken an implicit step in here, which has said m alpha becomes dm alpha, which is just the the density divided by a volume element. Okay. Actually, it's not divided by; it's multiplied by density times volume element. Forgetting my geometry. Okay, and you'll notice that I've reused rho here. Yesterday I was using it for the distance away from the rotational axis. Now I'm using it for the density. You're going to have to live with that. We're getting to the point in physics now where there's more things we have to assign variables to than letters we have available, and sometimes we have to reuse them. It's just got to be clear what we're going to do when we use them, okay? So if it's an ambiguous variable and you're doing an exam or an assignment or a tutorial, just spend 1 second to define what it is. Rho equals density, or rho equals distance from axis. That's usually enough to let someone know what your convention is in a particular problem. All right, so to get Ixx, we're now doing an integral over volume dv, and as you know from your real analysis courses, which you probably have as bad nightmares about as I do, this is now integral in 3D space, right? So this is now going to be integral from 0 to a, integral from 0 to a, integral from 0 to a of m over a cubed is our density, y squared plus z squared dz, dy, dx, okay? And if you don't know how to do this, make sure you know how to do it, because this is the main reason why we make you do real analysis courses. It comes up all the time in physics. What we can do is pull the constants out the front, and then we know the integral of a sum is a sum of integrals, right? So we can write this thing as m over a cubed triple integral of y squared dx, dy, dz. And of course, the order you do the integration in doesn't really matter, so I can write them any order I want. Plus triple integral of z squared dx, dy, dz as well, right? And of course, now I can break the components out into their individual parts in this as well, okay? So let me just slip this equals back over so I've got some room. So I've got m over a cubed. And what I'm going to do here is basically take this integral, and I'm going to assign the term in the front to each of its individual components, right? So what I've got is, when I switch back to the right color, integral over dx, integral of y squared dy, integral of dz, plus integral of dx, integral of dy, integral of z squared dz. Okay, pretty easy. And then this, of course, is going to be m over a cubed in here. This first term here just becomes a. This becomes a third a cubed, or 1/3 y cubed, which when I put a in, I get 1/3 a cubed. And then I'm going to get an a in here, right? So this is going to be a times a cubed on 3 times a plus a times a times a cubed on 3. So these problems usually fall out pretty easily like this. If we add all these terms up inside here, this is now 2/3 a to the power of 5 times m over a cubed. Okay, so you can see in here I've got a times a cubed times a is a to the 5th, and I've got a third for each, so that gives me the 2/3. Okay, and then in the end I can clean the a cubed in the bottom up, so this is now 2/3 m a squared. Pretty easy, right? And then what I want to do is get the other component in here, the product of inertia, this xy, and so it's minus sum over a, sum over alpha m alpha x alpha y alpha, which becomes actually let's just get rid of this bit and just go straight to the integral. It's now going to be minus integral of rho x y dv. Okay? All I've done is x alpha y alpha becomes x and y, and make the same substitution from mass to dm to rho dv on the right hand side. And of course I've got a minus sign in this term and not a plus sign, as we discussed on the last slide. Okay, So I can work this thing out, and it actually turns out to be a little easier now. It's minus integral 0a, integral 0a, integral 0a, m over a cubed, x, y, dz, dy, dx. Okay? And then in here, what I'm going to do is minus m on a cubed. And of course, I can do the same spread out that I just did. Okay, so this is now going to be integral of x dx, integral of y dy, integral dz, like so. Okay, I can leave the limits off now because I kind of have already written them once. I don't have to keep writing them again and again and again. And of course, spread the terms out in here now. So this is going to be a cubed. This thing is going to become a half a squared. When I integrate that up, this is going to become a half a squared as well. And this one on the end will become a. Okay, so then I can add all this up. This is going to be a to the power of 5, and the fraction will become a quarter. So this is minus m on a3 times a quarter a to the power of 5. And then, of course, I can clean up my a cubed in the bottom with the a5 on top. So I get minus a quarter m a squared in here. Okay, and I'll let you convince yourself that the other two moments of inertia, yy and zz, end up the same as x, and the other two the other 5 products of inertia, yz, blah 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 blah, all end up the same as xy, right? And you can see that just by looking in here that all the terms up in xy are going to look like this, and so the integral is just going to play itself out exactly the same way. And likewise, for this term here, you're just going to have something instead of xy in here, and the whole thing is just going to play itself out in a different coordinate, right? Now, the one thing you'll realize is if my limits are not the same in all 3 directions, in other words, I break the symmetry of the problem, then those components are not going to be equal, right? It'll play out the same way, but I'll have different limits, so I'll get a different answer. Okay, so what we just did relies quite heavily on symmetry, and so it's useful to understand how that propagates through the problem, because not I'm necessarily going to do it, but it's fair game to give you something that's got reduced symmetry compared to a cube here, and then the smart way to do it would actually be, rather than to work out all 9 components, would be to work out all the ones that are symmetric first, and then work out what are the ones that are in the broken symmetry so you can fill out the rest of the matrix. Okay? And so if we put this together, our matrix here now will be, we've got our moments of inertia down the diagonal, so this will be 2/3 ma squared all the way down the diagonal, and then we're going to have minus a quarter ma squared on the 2 off-diagonal sides. And the other way to write this would be to pull the common terms out the front. So we can pull an ma squared over 12 out the front. And the reason why it's 12 is there's a 3 in the denominator for the diagonal and a 4 in the denominator for the off-diagonal terms. So 3 by 4 is 12. That'll get everything to an integer. And so then our matrix here becomes 8, 8, 8, minus 3, minus 3, minus 3, minus 3, minus 3 down here, minus 3 down here. And you can see we've got this nice symmetric matrix that behaves itself really well. Okay. One last step in the question is to find the angular momentum when omega is along a particular direction. Okay? One really important thing to do, particularly in exams, is once you think you finish the question, go back and read the question and make sure that you've finished the question. There's so many people I've seen in the past who've done exams and kind of got to an answer and then just moved on and realized that, hang on, there was one extra bit that they had to do, but they just forgot that it was there, right? And given you're most of the way through this problem, it's actually probably not very hard to get to the answer, and that's true here, right? So what we're after is the angular momentum. And the direction that we have in the rotation here, let's call it u for a second, is basically the 1, 1, 1 direction, but we probably want to make that a unit vector, right? And so to make that a unit vector, we would normalize it. and you know how to do that, particularly for real vectors. It's kind of easy. We don't have to do any conjugates or anything like that. So this thing's going to be 1 over square root of 3, 1, 1, 1. You can convince yourself of that. Okay, so now our angular momentum is just going to be our angular momentum as a scalar times that unit vector for the rotation direction, and so it would be omega on square root 3, 1, 1, 1. Right. Angular momentum is I times omega. We'd have two vectors in here, and we know our I is a tensor in this particular case, or a matrix, and so we can pull this in. We can bring in the prefactors at the front, so this would be ma squared on 12, and this would be omega over square root of 3. And then we've got what you all know from linear algebra is just a matrix, which Adam has just set about to drawing horribly badly. And this is again another thing in exams. You have to write quickly, so you don't want to be, you don't want the perfect getting in the way of the good, because you'll never get it done. But there has to be a certain standard, because if it's all scrawled all over the place, the examiner's not going to be able to follow it. And if there's really big ambiguities, they're just not going to be able to give you the marks. So you kind of have to keep a little bit of neatness if you're doing exams, otherwise things get just unmarkable. Okay, so we got something like this, right? And now, as you all know, we would go through and just multiply the matrix by the vector. We've all done this multiple times, I'm sure. So this is ma squared on 12, omega on square root of 3, and if we take the row and multiply it and do that for each of the terms, so it's going to be 8 times 1 minus 3 times 1 minus 3 times 1, 8 minus 3 is 2. In the middle one, we've got the middle row comes up and gives us the second element, so it's going to be minus 3 plus 8 minus 3 is 2, and the bottom one is the same, so here's this nice clean vector. Makes sense. We would expect it to have some symmetry to it, and we see that symmetry in there, and then we can just clean this thing up a little bit. This is going to be ma squared on 6 omega, okay? Just using the fact that the omega is this vector here, and 2, 2, 2 is basically 2 times 1, 1, 1, right? So it brings a 2 out the front that knocks out the knocks the 12 back down to a 6, and everything cleans itself up there. Okay, fairly easy, fairly typical sort of. This one's almost an exam problem style. It's quick and easy to do. The symmetry's nice. It's designed to test your concepts without actually making you do massive amounts of work. An assignment problem would probably be more along the lines of removing all the symmetry in here and making you have to work a little harder about it. That's not to mean that you might not take one symmetry out just to check that you understand how symmetry impacts these things. It sort of depends on what the examiner wants to do, but this is very much in the style of an exam style problem if I look at it. Okay, so let's take a break there, and then when we come back on the other side, we'll go a little bit further with implications of inertia tensors.